So it's wonderful to be here at Know Thy Star. I am going to be primarily presenting work that's been led by my grad student, June Parsons, at York University. And we wanted to just play around with some hypothetical atmospheres that could exist in Earth-like planets orbiting brown dwarfs. Kevin just gave us actually already a wonderful intro to my talk. I think the organizers gave him my slides first and were like, here, just talk about all of this. Exactly, yeah. Let's break it down even more simply. So as we go from these hot F stars to M stars, broadly speaking, we're going from an environment of much more high near UV and less far UV, and then at the M stars it flips, right? You have a lot more far UV compared to near UV. And that really drives different photochemistry, as we'll see. And for substellar brown dwarfs, the UV is really, it's difficult, they're very dim, it's hard to detect. So there's uncertainties. But we really do care about UV. UV destroys molecules in the atmosphere, like methane, which is a biosignature, making it more difficult to detect. It produces other biosignatures, like creating ozone from oxygen. Now, I want to talk quickly about why do we even care about oxygen and ozone. I think a lot of astronomers don't know why we care about oxygen as a biosignature. And so just simply put, oxygen is produced from oxygenic photosynthesis, and that uses three very common things in the universe, right? It uses photons, water, and carbon dioxide. That's the feedstock molecules upon which oxygenic photosynthesis produces oxygen. And because it uses these really highly abundant molecules in our universe, it's become the single most successful biomass building product on Earth. So that's why we care about oxygen. We assume that other places might be able to figure that out because these initial components are so common. Now, it's not that we as complex life use oxygen. That gives you the biggest redox energy gradient. But for most of Earth history, we didn't have complex life. So that's not necessarily why oxygen exists. And then Kevin also mentioned this. Really, it is the ratio of far UV to near UV that matters, and where exactly is this UV? So if you just look at the rates of ozone production and destruction, you can see that to produce ozone, you really need far UV light, but to destroy ozone, you can do that with near UV light. And so this is why the balance of those two will ultimately determine, say, how much ozone you have in an atmosphere. Also, it's a small part of the flux UV, but it's really critical to photochemistry. So this is just from M stars, where we have more data, but you have the muscle observations here, and it's a small component of what's the bolometric flux coming into the top of the atmosphere, but it really drives all the photochemistry. And you can, as Kevin also already mentioned, muscles showed that quiescent M dwarfs are very similar to flare stars, more similar than they are not. And so here you can see some models from AD Leo, a very bright flaring star, versus a completely inactive photosphere only from Phoenix. And then these are the muscle stars put there. So they're just a lot more similar to a flaring star than to, say, something with no chromospheric activity. And if we were to compare the really extremes of UV here, I just want to make this point that your this is the same planet. This is the same planet orbiting the same spectral type, but just changing the extremes of UV. And you can see that what is in the atmosphere changes because of the destruction or the lack of destruction by UV. So this is otherwise the exact same outgassing on a planet. So it just is, UV really matters. But as we know, M stars may have problems in retaining their thin Earth-like atmospheres. We're seeing a lot of observations that are showing atmospheres are consistent with nothing. So then there's a question of, well, maybe, I don't know, maybe would brown dwarfs be better? Would maybe you be able to more retain atmospheres of brown dwarfs? Now, brown dwarfs also face challenges to habitability. They continually cool, so their habitable zone is moving inward over time. And we're not sure whether water will be retained, because that really does depend on how much UV flux is in the atmosphere next to UV. But it seems like they might be more likely to retain atmospheres than M dwarfs. They don't have the same problems. So we wanted to look at 3 models of UV for brown dwarfs. So one is just using Phoenix photosphere only, no excess UV as the very lower limit. More likely perhaps is, say, something like a Jupiter Aurora UV model for brown dwarfs using observations from Jupiter. And then also noting that Jackie Faraday, they found on cool brown dwarf evidence of methane. Well, they found methane emission, which is possible evidence of aurora on a brown dwarf last year. And also a third UV model we looked at was extrapolating UV from one of the most quiescent M stars, GJ1214. So we put these 3 UV models with 4 different brown dwarf temperatures, as the brown dwarf is cooling. As this is, what's the input of the model. And so you have the Aurora model, the Mussels model, and then, like I said, the Phoenix model in green here. And then just at different temperatures going from 2500 Kelvin down to 700 Kelvin. If you want to think about it another way also, because the brown dwarf is steadily cooling, this could maybe represent like a progression of UV as it's aging for each model. So these are just some preliminary results of maybe what an Earth-like atmosphere would do under these sorts of UV environments. And so here in this column, we have the temperature pressure profile, and then we have mixing ratio columns here for ozone, OH, the hydroxyl radical, water, and methane. I wanted to highlight I'm going to kind of tease out ozone today only, and see that just as, of course, when you don't have a lot of UV, you don't produce much ozone. So you can see for the most minimal UV Phoenix models, the ozone is much, much less, orders of magnitude less. And then we have the black line sun for comparison. And as you go to the higher UV models, you get even more ozone often than even the sun. Methane is also interesting. You can see that our sun destroys a lot more methane than would be destroyed around these sorts of brown dwarf systems. So then if we look at what the hypothetical transmission spectra is for an Earth-like planet orbiting the brown dwarf and the sun, here I'm just going to highlight out, again, the ozone feature. And you can see the Earth-Sun system is in black, and then you have our Earth-like planet orbiting the brown dwarf in these other colors. So the green, much less ozone production, and versus the Mussel stars and Aurora model brown dwarf extrapolations have more ozone than even the Earth-Sun system. And this is just showing that more highlighted the difference in the transmission effective height compared to the sun. So this is just doing the difference with compared to our sun ozone feature, and you can see that except for the Phoenix models where you have much less ozone production, you actually do get quite a bit more ozone. Now I wanted to also just take 2 minutes to talk about something, because I saw in the next session after lunch there's future directions and future missions, and I'd be horribly remiss to not mention my favorite mission at least once, which is the LIFE mission. The LIFE mission, it's the best acronym ever, right? Large Interferometer for Exoplanets. It's a in-space nulling interferometer mission designed to try to detect a statistically relevant sample size of Earth-like planets to be able to detect biosignatures. So inhabitable rocky planets that have the size and installation similar to Earth. And so basically what this is doing is using a nulling interferometer to put in a phase inversion, and then you can see here, if we go back and forth, you can just null out the star and directly image the planet. So that is the goal, and I'm really excited about it. And so I just wanted to at least give a shout out to that, because I do think it's one of the best efforts we'll have to try to detect biosignatures in Earth-like planets, and hopefully it'll fly in the next couple of decades. It's also a very complementary mission to the Habitable Worlds Observatory. I love UV, so I also am super excited about the Habitable Worlds Observatory. But just to highlight, the Habitable Worlds Observatory is going to really have a hard time getting CO2, methane, and the surface temperature, and especially those things are very important molecules, whereas life will be able to get the surface temperature and carbon dioxide, methane, and ozone, but it's not going to be able to get oxygen, the O2A band. However, ozone is a really good proxy for oxygen, so it's just a very complementary mission. This is our little schematic of it. And so going back, though, to the reason why I was invited, brown dwarfs might have habitable planets. They have their own but different issues than M-stars. Their UV environments may vary substantially. We're still at the infancy and trying to figure out what the UV environments are for brown dwarfs. I would say this conference should be Know Thy UV, Know Thy Planet, because that's such a strong influence on our planet environment. And life is a cool mission concept that you should follow and get on our mailing list and keep apprised of that. All right, thank you. Huh? Yeah. Yeah.
Do we have a mic down here?
So you're absolutely right, Sarah. I should have put life in the session. It's totally my fault. My apologies.
No problem. Just.
Hi, it's Dave Wilson, University of Colorado. So do any of these models turn into an observable flux? Are there any brown dwarfs where you could possibly observe it in the UV?
So our constraints, there's a few measurements, but not much, is my understanding. So like that methane feature, that's in the IR, but that's like a proxy for activity. It's really hard. They're so dim, yeah.
Hi, really nice talk, Kaz Gary, Ohio State. I had a question about the point that you made about habitable planets around brown dwarfs. Besides the gradual cooling in the habitable zone going inward, are there any other factors about brown dwarfs that would make planets around them not as habitable, or would it affect the habitability?
Absolutely, they do have problems. Mainly the tidal heating, because they're so close in. That might change where you need to put your planet, because you just get so much heating. So in order to not trigger a runaway greenhouse effect, you need to really you have to have very circular orbits, depending on that. So yeah, so the tidal heating effects are really important to look at, and I would recommend that paper by Rory Barnes and Renee Heller on brown dwarfs. It has a nice summary of that effect and looks at those things. Thank you.
I'm just curious if you thought about the effects of particle radiation as well, because like the moons of Jupiter are exposed to a super harsh radiation environment. If the UV is coming from an aurora, it has to come from that aurora radiation environment. So I'm just curious if you thought about that at all as well.
I missed the first part of the question. Is consider the flux from particles or from aurora?
Right, the particle radiation environment that's trapped in like the potential magnetic field of the brown dwarf.
Yeah, no, absolutely. Yes, corpusculars matter. We have not added those in, but they do matter, and I think they actually matter more in many ways more than the UV, especially given that these habitable planets would be quite close in. They're just more difficult to model, but definitely.